One-to-one functions never assign the same value to two different domain elements. Definition: a function f is said to be one-to-one, or an injunction, if and only if f of a equals f of b implies that a equals b for all a and b in the domain of f. A function is said to be injunctive if it is one-to-one. Let's take a graphical look at this example. If we've got a, b, c, and d in the domain, and 1, 2, 3, 4, 5 in the codomain, and we map, say, a to 4 and b to 5, d to 3, and c to 1. This is one-to-one because each element in the codomain maps to only one element in the domain. If we did something like b instead of, well, let's rather than change what's there, let's put, say, another element out here. We'll make that e. And if we made e also point to number 5, then in this case, this would not be one-to-one because we would have two different elements from the domain mapping to the same element in the codomain. So we cannot have that. Note that a function is one-to-one if and only if whenever a equals, whenever a is not equal to b, then f of a is not equal to f of b. This is the contrapositive of the definition. These two definitions can be expressed as for all a, for all b, f of a equals f of b, then a equals b, over the domain of f. And the contrapositive as for all a, for all b, if a does not equal b, then f of a does not equal f of b. Let's look at an example. Determine whether the function f from the set a, b, c, d to the set 1, 2, 3, 4, 5 with f of a equals 4, f of b equals 5, f of c equals 1, and f of d equals 3 is one-to-one. And this is one-to-one. And why is this one-to-one? Well, in the image, there are no two values from the image that map from the same value in the domain. So all image values map to one and only one domain element. In the next example, we'll determine whether the function f of x equals x squared from the set of integers is one-to-one. And this is not one-to-one because we can take f of negative 1, and that is equal to 1 squared, which is equal to 1. And we can also take f of 1, which is equal to 1 squared, which is equal to 1. And that gives us two elements from the image, which map back to different elements from the domain. Therefore, this is not one-to-one. The next example is determine whether the function f of x equals x plus 1 is one-to-one from the set of reals to the set of reals. And when you suspect a function is going to be true, sometimes it's easier, rather than to try to prove it directly. In this case, you'd have to try to prove it for every element. Instead, we can look at the contrapositive for this and go, okay, so when x does not equal y, then x plus 1 does not equal y plus 1, which is obviously true. So just approaching this from that contrapositive allows us to solve this very simply, whereas solving it in a direct method would have been much more difficult. Increasing and decreasing functions definition goes like this. A function f whose domain and codomain are subsets of the set of real numbers is called increasing if f of x is less than or equal to f of y, and strictly increasing if f of x is less than f of y, whenever x is less than y and x and y are in the domain of f. Similarly, f is called decreasing if f of x is greater than or equal to f of y, and strictly if f of x is greater than f of y, again, whenever x is less than y and x and y are in the domain of f. So we can write this as the function f is increasing if, for all x, for all y, if x is less than y, then f of x is less than or equal to f of y. Strictly increasing if, for all x, for all y, x is less than y, then f of x is less than f of y. And decreasing if, for all x, for all y, if f of x is less than y, then f of x is greater than or equal to f of y. And strictly if, for all x, for all y, x is less than, if x is less than y, then f of x is greater than f of y.